So today we start a new topic, which is the concept of path integral. We start with going back to the problem of quantum mechanics of a single particle, okay? So for the time being, until we'll get there hopefully by the end of this lecture, let's forget about the many body thing, interactions and all that. Just a quantum problem where you have a Hamiltonian of a single particle, a single degree of freedom with kinetic and potential energy, and the path integral is an alternative approach which Richard Feynman has proposed to describe quantum mechanics. It's not a different theory, it's a different formulation and a different technical approach, if you like, to solve problems in quantum mechanics, which turns out very useful for certain things. I will get there and I'll explain in what way is it more useful than solving Schrödinger equation, which is what we learned to do so far. And in addition, it's very intuitive. It really brings forward the intuition behind the quantum world as much as we can develop intuition too. Okay? So let me first mention the problem that we are discussing. We have a Hamiltonian that is made of a sum of two terms, kinetic energy, which is just p squared over 2m, okay, and p is a momentum operator. It's also one-dimensional. There's only one coordinate and its conjugate momentum, and v is some function of the coordinate. Okay? Okay, and P and Q obey the usual canonical commutators. IH. Okay? Very good. So first of all, I remind you what did we do in your undergraduate courses. You learned how to solve such problems for particular choices of V. And the approach was to solve the Schrödinger equation, right? You look for basically some eigenstates of the Hamiltonian, and find the energies and the states, and then you, in principle, know also how to solve problems like time evolution of a particle, because once you know the eigenstates, you can write any state as a superposition of eigenstates. And then you know how they evolve in time. There's just a phase factor, e to the minus I epsilon t over h bar, and you know you can solve a lot of problems. But what we're going to do now is to consider indeed a problem of time evolution. And the path integral formulation is going to provide a nice way of describing it, which is kind of intuitive. So let me first draw here the line Q is the coordinate, and we'll introduce another axis, which is the time evolution axis. Actually, let me maybe draw it opposite way, so this will be Q, and this axis will be the time evolution. This is the time axis, and this is t equals 0. And we imagine the following problem. Let's assume that we start from a wave packet where we prepare the quantum particle at t equals 0 in a particular coordinate qi, okay? And we prepare a state that is localized, completely localized at qi. So its initial wave function is a Dirac delta function. Okay? So this is how it looks like. Okay. More or less, it's a delta function localized at qi. And now we let it evolve in time. And when it evolves in time, it changes, right? Because our Hamiltonian contains a kinetic energy, which depends on the momentum, and momentum is not commuting with Q. So this state, this initial state, is not an eigenstate of the Hamiltonian. It will evolve in time, and in particular, it will spread in Q in some way, and all that depends on the potential, right? So, quite generally, if we look at later and later times, so let me first write here the formulation of the problem is such that we prepare the initial state is going to be the state qi. Okay, I'm writing it in a bracket notation, but this means a state that is a delta function at qi. Okay, this is the initial state. What is going to be at finite time? It will evolve, and we can actually express this psi of t as e to the minus I h t over h bar times qi. Okay, so in other words, we take the initial state and we apply the time evolution operator, right? And this will give us a solution of the time-dependent Schrödinger equation, psi of t. And now what we're going to do is to evolve this state until we reach some final time where we want to make a measurement. Okay? And the measurement we're going to make is to measure the state or the probability to find the particle at a particular coordinate, which is generally different from qi. Okay? Now, how does the wave function look like as a function of time? So, if we look at a slightly later time, now it's going to be something like that. And then later it's going to be something like that. Okay? And we do it for many different times. And now I'm going to look at some final time. So this is at t equal capital T. Okay? t equal capital T, and we again plot the q-axis, and I see that the wave function now has some, if you look at the absolute value square of it, it's going to have some value at many different q's, right? It's no longer localized, but now what I do is I make a measurement. Let's say I choose some qf, generally different from qi, and I make a measurement. Okay? What does it mean to make a measurement? I take the final state, which is psi of t, and I project it on a state with a well-defined coordinate qf. Okay? And the amplitude for, let me write it like this. I define here a function g of qi, qf, and the time that elapsed from the initial condition. And this is going to be the projection of the state psi of t on qf. And it's just the amplitude. If I want to know the probability to find, again, to find the particle, if I started at qi to find the particle at qf, the probability is going to be the absolute value square of this. So this is an amplitude. It's still something that can take complex values. And this object, this g, is called a propagator. Or a Green's function. That's why it's denoted by G, although in some books it's denoted by K, but we'll adapt G, okay? So and this is, if you like, this is a definition. But now, keeping in mind that what is psi of t, it's the time evolution operator acting on qi. I can basically rewrite it as a matrix element of an operator. And it's the matrix element between qi and qf, initial and final. Okay? That's what it is. And the operator that comes in, of which I have to calculate the matrix element, is an exponent of the Hamiltonian. Sorry. It's not just, so little t denotes here a continuous variable that goes from 0 to capital T. Here the argument I define as capital T. So this is its particular value at time equal capital T. Okay? So, I mean, of course, what I wrote before is true if I denote an argument by little t, but I want to use little t as a dummy variable that changes between the initial and final. Okay? All right, so in principle, we can compute this propagator by using the method I mentioned before, solving the Schrödinger equation, writing the state in terms of the eigenmodes, and it's going to give something. But what I'm going now to show you is that you can express this thing as a multidimensional integral quite generally, regardless of what is the Hamiltonian, what is the potential V, I can express it in a way that provides some intuition about what happens to the quantum particle as it evolves. Okay? So, all right. What do? We do the following trick. Okay? So here I'm describing a time evolution over some time capital T. I can look at it, I can split the time evolution to very, very short time windows. Okay, let's imagine that. Why do I do it? Because notice that when I look at the time evolution operator, it's an exponential of something that grows with the time. If I look at a very, very short time interval, I get an exponential of something small, okay? And if this thing is small enough, then the exponent is almost 1, right, to an extent. So what I'm going to do is, let's divide our time axis to small windows, which I denote by dt. And in the end of our process, I'm going to take the limit that dt goes to 0. It's infinitesimal. And to do this, I have to introduce, in order for dt to go to 0, I have to introduce here an infinite number of time slices. So I define here capital N to be t over dt. This is the number of time slices. And we'll do everything for finite n, but in the end, for a given capital T, I want to take the limit that n goes to infinity, which is equivalent to saying that dt goes to 0. Okay? Welcome back. Okay? That's the idea, and now let's see how we do it. So I'm taking the time evolution operator, and I'm now going to write down an approximation that I'll justify in a minute. I want to look at the full time evolution as a product of time evolutions applied one after another. And because I have n time slices, it's going to be e to the minus I h dt over h bar to the power n. Okay? Now, why do I write here an approximation sign and not an equality? Why is it not an exact relation? Because, I mean, if h was just a number, then, of course, the product of this gives you an exponent of the sum. An exponent of the sum will give us the full time evolution. Why is this an approximation? Because h is an operator, and it's an operator that includes kinetic and potential energy, which are not commuting. Okay? Now, there is a very useful formula that if I'm writing I have two operators, A and B, and I look at the exponent of A plus B. This is not equal to e to the A times e to the B. It's equal to this plus the correction, and the correction is, let me just make sure I write the, yeah, so just want to make sure that I have the sign correct. It's e to the A times e to the B times e to the minus 1/2 A B, and actually this has some actually has even some corrections, but for the case where AB commutator is a constant, you can stop it here. Okay? So now, in our case, what I'm claiming is, so what do we miss when I write e to the sum by a product? I miss the commutator. Yes?
But the commutator is 0, isn't it?
No, because, okay. So the commutator is, so the commutator, you're saying it's 0 because it's the same Hamiltonian.
Yes.
It's the same Hamiltonian. But the Hamiltonian itself, the problem is the Hamiltonian itself, it's sitting for a moment.
Oh, it's dependent. I mean, each step the Hamiltonian is changed. Because
What?
Each time step the
Okay,
Hamiltonian changed.
so yeah, the Hamiltonian. So we are working in a Schrödinger picture where the Hamiltonian itself does not depend on time, okay? Or the coordinate and momentum do not depend on time. So, okay, at this stage you are right, but we are going to use this. Let's here put an equality, but then what I'm going to do next is to split each of these exponents to kinetic and potential, and that's the place where we need the approximation. Okay? So you're right. If the Hamiltonian is not time dependent, which then complicates things, then this is still an equality. By the way, this is called the Hausdorff-Baker formula, and it's very useful. I want to mention in passing that in the website, in the Lambda, I posted a file with useful formula. This is one of them. There are others that we have used in the previous lecture, so just for when you need it for you may need them for your home. Okay. Okay, so this is what we do. First of all, we introduce this.
By the way, Efrat,
yes?
There is an operator that does not commute with itself, which is the displacement operator. If you take it for different p's, it's still, I mean, it's the same operator, but the p are different, it's not commute with itself. The displacement operator.
Yeah, no, that's true. That's true. But yeah, right. But in any case, there's something I want to mention. Okay, let's now do the next step, and I'm claiming that this connection, even if it's not exact, in the limit where dt goes to 0, it's becoming exact, and that's because the commutator always is higher order than the operators themselves. Namely, notice that what you have in the exponent is something that is linear in dt, right? The commutator already goes like dt squared, right? And the corrections, if there are corrections, will go like higher powers of dt. So in the limit that dt goes to 0, it's actually 0. You can basically eliminate the commutator and you're just replacing a sum by a product. Okay? Now let's look at each of these time steps and see what we can do with it. So I think I can erase this. Let me just write down. Let me just write down the definition here somewhere. So G of Qi, Qf. This is just the definition. Okay. This I will leave for now. So now what I'm doing, let's write what is e to the minus I h dt over h bar. It is e to the minus I t plus v dt, and t and v do not commute. Okay? So, however, that's exactly where we can make the approximation that this is okay, and t is just a function of the momentum times e to the minus iv, which is a function of only q, times the commutator, exponent of the commutator, sorry, so it's t v, but now here I have dt squared, okay? And then I also have additional corrections, but this is already smaller than the two exponents, okay? So in the limit that dt, so this thing actually goes to 0 or goes to 1 in the limit that dt goes to 0. Okay? So we are going to replace the time step by a product of two exponents. One is only including potential energy, one only kinetic. Okay? Let us rewrite the propagator. So it's going to have the following form. Here I have e to the minus I t, e to the minus I v, and then I have this is the first, and then I have capital N times the same thing. It's a product of e to the t, e to the v, alternatingly. And in the nth step, so here I have n such terms. The last one I close with qi. And if I'm looking at the nth state, somewhere in the middle, I have here okay. And then it's repeating itself. But at this stage, I didn't gain much. I just replace an exponent of a sum by a product of exponents. Okay. But what is the advantage of writing it like this? I now see that each of these operators, one depends only on Q, and one depends only on P. So I know that the eigenstates of this one are Q, the states Q, and all eigenstates of this are states with a well-defined P, right? And what I'm going to do now is to introduce in the middle between the two operators, I'm going to introduce a resolution of identity which projects them on their eigenstates. Okay? So, yeah. So this is basically what I'm doing. I'm going to try to leave enough space. Actually, I no longer need this formula because I believe I convinced you that we can make this approximation, okay? Okay, so what do we put here? It's a resolution of identity. A resolution of identity is something you can always put somewhere because it's just one. But I'm choosing a very particular resolution of identity, which is an integral over dpn going from minus infinity to infinity, assuming that my q and p, both of them go from minus infinity to infinity. It doesn't matter. Okay, and now I do Pn, Qn, okay? And I think you agree with me that this is a resolution of identity, right? In fact, there are two of them. One where I put the projection on Q and one on P. Now the index n, little n, is going from 0 to capital N, okay? Because this is at some intermediate time step in the middle, okay? So I put here a resolution of the identity which has this structure, and I see that, and now I do it between this time step and this time step. I put it between one exponent and the other, but then the next will be to the right of this. I have another e to the minus it for the n minus 1 time step, right? So let me add it.
But what about the constants in the middle?
Which constants?
The projection of Qn on Pn.
This, first of all, this is, we know exactly what it is.
Except for your curve.
It's just, so we know exactly what it is. Q is, so P is a free particle wave function, right? In a bracket notation, if I project P on Q, actually, this is, okay. I'll get to it, okay? But this is nothing but the wave function of a free particle, okay? Or the star, the complex conjugate, okay? Okay, but I'll get to it. But importantly, it's a number.
Yeah.
Not only it's a number, it's a function, it's a known function of a simple and known function of P and Q. Okay? But we are still not done. We still have some operators we need to deal with. And let me erase this because I need the space. Okay, so now here I'm going to have another pair of exponents and another e to the iv dt over h bar, where this now belongs to the n minus 1 step, and this guy already belongs to the n plus 1, right? If I'm starting from the right, so little n changes from 0 to capital N, okay? Now, here I can, between this exponent and this guy, I can introduce another resolution of identity. Okay, and that will be the, let me call it, this is Q.
Where are you putting the new?
Sorry. I put it in the wrong place. Sorry. Yeah, sorry. This we already took. This is what I want. Okay. Between the nth time step and the n minus 1. So, so here, when I put this resolution of identity, gave me a state. The Qn comes to the left of this, but to the right of it, I'm going now to introduce. So let me call it n minus 1 and Q n minus 1, and both of them going from. Okay, this is not important, and now I'm writing it like this. It's Q n minus 1, Q n minus 1, P of n minus 1, P n minus 1. Okay? And the same thing I'm going to do here. Okay? I'm not even writing it, but I put the same resolution of identity here with a different, with a P n plus 1 and a Q n plus 1. Okay? Now, what do I get after I finish? Okay? Let's just look at the two exponents that I have in the nth step. After I'm done with all these resolution of identities, I see that e to the minus iv dt is going to be sandwiched between Qn and Qn minus 1, right? And this is going to be sandwiched between Pn and Pn plus 1, right? And then we have another state, and it will repeat itself. So at each n step, I'm going to get the following expression. For that we need to erase something. Erase. Let me erase the figure. And what I'm going to do now is to write an expression for G of Qi Qf T, which after I'm done putting all these resolution of identities in between each operators, what I'm going to get is just a product of many things, but all of them are C numbers, are no longer operators. So at the end I have a Qf, and I have here things and things. Now let me write the nth step is going to be Qn plus 1 Pn plus 1 times the matrix element Pn plus 1 e to the minus I t dt over h bar Pn. Then I have Pn Qn. Then I have Qn e to the minus I v of Q sandwiched between Qn and Qn minus 1. Okay? And then it continues. This will be Qn minus 1 and blah, blah, blah. And after, so what these dots describe a bunch of operators which I sandwich with the resolution of identity. So just the unit that what I'm writing here, this expression will just repeat itself until at the end we're going to close it with a Qi and a Qf. Okay? Is that clear? Okay, so what I wrote here is just the nth, some little n between 0 and capital N.
Don't you need the integral?
Yes, yeah, thank you. You're right. So these are the states, and you're right. Yes. Forgot to write it. Yeah. So allow me the integrals to send it to the left of the expression, okay? Because everything depends on it here. So write it there. Okay, so here I have integral of, actually let me write it as a product of n going from 0 to n d Pn d Qn, and all the integrals go from minus infinity to infinity, but I have an capital N integration steps, okay, over the momentum and coordinate at the nth time step. Okay, this is what it is. Okay, all right. Now, what is nice about this is that everything I wrote here is a C number, and we know exactly what it is. Okay, so I'm going to replace this by a function. A function of what? Of the variables Qn, Pn, and so on. Okay. Let's see one by one. First of all, what is this? It's a matrix element of an exponent of an operator for which Qn minus 1 is an eigenstate, right?
Maybe
So
you took so much to the left.
what?
You have like an extra product to the left.
What?
You marked the entire purple thing.
So the purple thing is just a product of 4 objects.
Ah, okay.
Okay, and this already belongs to the next one. Okay, which has the same, exactly the same shape, but it's
Yeah, okay.
the n plus 1, and this is the n plus n minus 1. Okay.
Okay.
Okay. Right, and in the end, you always have to end with something that gives you a projection. Like, for example, the q n equal 1. Actually, n. Yeah, if I want to be a little more careful, n goes from 1 to n, but then q0 sandwiches with qi, and q0 equals qi. Okay, but okay. Never mind. Okay, so it's it doesn't matter, because in the end we are going to take capital N to infinity, and dt is going to be something that will turn into an integration variable, because we're going to have a continuous time evolution from 0 to capital. Okay? I want to be a little careful. That's why it's cute. Okay, so what is this thing? First of all, let us look at the matrix element, this one. What is this? So, because Q, a state with well-defined Q, is an eigenstate of it, it gives you nothing but e to the minus I v of Qn minus 1 dt over h bar times a delta, because after I replace it by its eigenvalue, I get Qn minus 1, and it gives me a delta, right? Because it's an orthogonal state, so it gives me a delta of n, a delta of Qn and Qn minus 1. Right? Okay, which means that I actually can change the variable here to Qn. And so let me do it, because I want to keep it the simplest expression. And what is this? It is just a function. Now v of Qn is just the value of the potential at Qn. Okay, so it's a number. Similarly, I can rewrite this guy. this matrix element. Now the same story, but here there are eigenstates of P. So this is going to be replaced by e to the minus I t of Pn dt over h bar times a delta of Pn plus 1 and Pn. Okay? Okay, great. Now we are left with the overlaps of, or the matrix elements of Q and P and Q. And this is where I remind you that in the if I write the P, Q, what is this? It's a projection of a state with well-defined P, namely a free particle with a state at coordinate Q. So this is nothing but the coordinate representation of the free particle wave function. And we know that it's some normalization factor times e to the I p q over h bar, right? That's what it is. Now, what is the normalization factor? The normalization factor that we'll need here is going to be 1 over 2 pi h bar. Okay? Why is the 1 over h bar here? Because notice that when we introduce the resolution of identity, we integrate over p and q. It has dimensions. So I need the 1 over h bar to get something that is dimensionless. Okay?
Of course, we can do that with the wave number, right? Instead, and
yeah, you can do it with the wave number, but I want to use momentum. Okay? Okay? All right. So this is exactly what we have here, but notice that in one case the p is on the left, and in the other it's on the right. So if we carefully replace them by this wave function expression, we get that this is going to be, it's the complex conjugate of the free wave function. So it's 1 over 2 pi h bar times e to the minus I Pn Qn over h bar. Okay? What is this? Now it's exactly the overlap of a Pn plus 1 and Qn plus 1. However, notice that we have here a delta of Pn plus 1 and Pn. So with your permission, I will replace this Pn plus 1 by Pn. Okay, I'm using the delta, and I get 1 over 2 pi h bar times e to the plus I Pn Qn plus 1 over h bar. Okay? Okay, so there are two places where I use this the deltas. Okay, here I write everything in terms of the coordinate Qn. This is the same Qn, but this is already Qn plus 1. Okay? And this Pn will go all through here. Okay? Okay, so I got a product of 4 things, and let me write them, the final result. So with your permission, I erase everything that is here in the middle. and just replace it by the product of these four things. But you see that here I can already collect them together in a compact way, right? Because, first of all, if I look at the exponent with the potential energy and the kinetic energy, now V of Qn and T of Pn are C numbers. So the product of the exponents is the sum, okay? This is now an exact statement. And then what I'm going to get in the exponent, if I unite them, is just T plus V, which is the Hamiltonian. The Hamiltonian were calculated at Qn and Pn, right? So let me write use the color red to write this exponent will give me e to the minus I h of Pn Qn dt over h bar, where h of Pn and Qn is just a classical Hamiltonian, if you like, because it's a function of the two variables. Okay? And now I'm uniting, this is multiplied by the product of these two exponents. So I'm now uniting them. And when I unite them, I see that here I have, and again, I can use the fact that the product of the exponents is the sum. What is it going to give me? Apart from a factor of 2 pi h bar square, it's going to be an exponential of I Pn over h bar, but now if I unite these two exponents, I get here Qn plus 1 minus Qn. Okay? Okay, great. It's progress. And of course, these two exponents, once again, I can write them as a sum if I like, because everything now is numbers. So what we did in our process, we essentially eliminated the operators. Okay, we eliminated the non-commuting object, and mathematically, the price we pay for it is that we have an integral over many, many variables, and in fact, we are going to go to the limit that n goes to infinity, so that the number of steps is infinite, and in fact, so it's if you like, it's the continuum limit of a product of integrals. Okay? So we are integrating over infinitely many variables, but the correct way to think of it is a multi-dimensional integral, but taking it to the limit, the dimension is infinite. And I'll relate it to some intuitive picture, but there's still a nice way of simplifying the whole thing even further, because what we have here in the exponent is the difference between Qn plus 1 minus Qn. What is it? It's the change in the coordinate between two time steps separated by dt, right? So I can do the following trick. I can multiply it by dt and divide by dt. Okay, I didn't change anything.
You get the derivative.
Exactly. So now Qn plus 1 minus Qn over dt is nothing but, in the limit that dt goes to 0, which is where we are heading, is going to be the derivative of q with respect to time, and the whole thing will be multiplied by dt, right? Which is also what we have here. So we can unite these two exponents and replace them by dt over h bar times something.
So that's the Lagrangian, right?
Almost, yeah, right, yes. You see already the next step, so let me just repeat. So what I'm doing, I'm going to replace this by qn dot, okay, time derivative, and then let me rewrite now the propagator. What I'm getting is that g of qi, qf, and t is, first of all, I have here some integral of a product, n goes from 0 to n of dpn dqn divided by d 2 pi h bar squared, but this repeats itself capital N times. Okay, let me maybe do this just to not to confuse. And now I have sandwich between the qf. So actually, not even that. After I'm done with all the matrix elements, I close it on the right and left with qi and qf, and all I've done is equating q0 to qi and q capital N to qf. Okay, so there is a constraint on this integral that the q 0 is going to be identified with qi, and q capital N is identified with qf. And what I have in the middle is a product of all sorts of things, but what I have in the nth step, I have e to the minus I, sorry, let me write it like this. It's e to the I dt over h bar of pn qn dot minus h of pn qn. Okay, maybe I'm just not to confuse, let's write it like this. Okay. This is in the nth step, but I have this going from n equal 1 to n equal capital N, okay? And exactly as Joseph said, this is nothing but the Lagrange, or basically the Legendre transform. It's the Legendre transform, okay? So, which is, okay, let me just call it L. But I still don't want to call it a Lagrangian because it's still dependent on both P and Q, okay? And we'll have to do one more step to get to a Lagrangian, but this is where we're heading. Okay, so this is, let me call it Ln for now. And now, what I have here is a product of such thing appearing in the exponent, but they are all numbers. Because they're all numbers, I can replace the product of exponents by an exponent of the sum, right? And in the limit that dt goes to 0, which is the continuum limit of this index little n, we're going to replace Pn and Qn by, and this is for dt goes to 0, we're going to replace it by P of t and Q of t. Okay? Now they're going to be the coordinate and momentum at time t. Okay? In other words, what is actually Q of t? Q of t is a trajectory, right? It's the coordinate is a function of time, and it's a number, no operators. Okay, it's like in classical mechanics, if you will. So when I'm done with all this, let me write what I get for the propagator. I think I can erase this already. Clear the space. And I'm getting let me write it P Q. I will define this capital D. You see, this is a differential, a generalized differential, which actually is dependent on variables that themselves are functions of time. I'll define it in a minute, but what I have now in the exponent, the functional that I'm going to integrate over is e to the I over h bar integral dt from 0 to capital T of p q dot minus h of p and q. Okay, and on the integral here I have a constraint that q0 p0 sorry, q0 is qi, q of capital T is the final coordinate. So I'm integrating, I have constraints on the beginning and end, but in the middle, q of t can be any function of t. I'm actually integrating over all the possible trajectories, okay? We still have one step to follow before we get there, and then we'll, which is to do the integration over p. Okay, that step we can do exactly. Okay, and this already looks like a Lagrangian integral over time, what it will give? An action, okay? But we still need one more, and I have to define what is the differential. So dpq is actually the limit when n goes to infinity of, first of all, 1 over 2 pi h bar to the power 2n, yes, times product of dpn dq. Okay, it's just this. Yes.
So we are taking P and Q in the real numbers, right? So
Yes.
we don't care about cardinality at all, right?
About what?
Cardinality, because we are making products on natural numbers.
Yes.
So we are saying that, like, we are doing a physicist approximation to real numbers, or when taking the limit. Because
I'm not sure what you mean. By definition, P, these are numbers.
Right.
Right, they are numbers. They are just values of Q and P at some time steps. And then when we take the limit that dt goes to 0, it's going to be, these variables are changing smoothly as a function of time.
Okay.
Okay, so in fact, that's all. I mean, but there are numbers all along. So the trick that we did, the main trick was just the fact that we did this incremental, very tiny time steps, allowed us to sandwich all the operators between quantum states with well-defined momenta or coordinate in such a way that we got rid of the operators just because we shrinked the time step to 0. That's essentially the mathematical step, and I don't know if mathematicians would probably faint if they see that. I mean, they don't. No, I don't know that it's mathematically, but essentially, when I write it like this, you understand what I mean. Okay. You define it as a discrete thing, and then you go to the limit that some variable is going to infinity, and actually even numerically you can define it by an approximation. So okay, now we miss one step is that in order to be able to replace this object by a Lagrangian, as you remember from the initial lectures of this course, the Lagrangian depends not on coordinate and momentum, but on coordinate and its time derivative. So we want to get rid of the integral over P. Okay? And we can do it because, why can we do it? It's actually very simple, because the P dependence of H is very simple. It's just a Gaussian, right? It's a P squared. So if we look at let me write down at each time step. So here P, there is a Pn where little n goes from 1 to n, but let me just pick one particular n and call it P. I have here the integral from minus infinity to infinity of the variable P of 1 over 2 pi h bar. 2 pi h bar e to the I dt p q dot minus the kinetic energy p square over 2m over h bar. Okay, right? That's what I have. So here, actually, I went back to the discrete description. I just took one time step, and I integrate only over p. I leave the q outside. Okay, the q is still left. I still will have to integrate it in the end.
You intentionally split it
What?
You intentionally split it from the.
Yeah. Actually, I should have done it before I went to the continuum limit. Okay, sorry if I confused it, but I look only at a single variable.
Yeah,
okay.
Only the kinetic part.
Only the kinetic part, of course. This whole thing is going to be multiplied by e to the minus iv. That I leave outside. I only take here the part that depends on p. Okay?
We can think of that as the Fourier transform of a Gaussian, right?
Yes, yes, but notice there's one thing to be a little careful about. there's an I here, so it's a Gaussian, it's a analytic continuation of the Gaussian to the complex plane, but it's still fine if you introduce an epsilon. Okay, let's not worry about there are some mathematical things that I put under the rug, but they are well defined if you do it carefully. So this integral we know to solve, right? What is it? So I'm reminding you of a Gaussian integral. If you have an integral from minus infinity to infinity of e to the minus a x squared plus bx, okay, that gives square root of pi over a times e to the b squared over 4a. You're familiar with this?
Yeah.
Okay, so this is what I'm doing here, and let me write down the result with all the normalization. So it's m over I 2 pi h bar dt times, and now what is my linear term with the b is actually q dot dt over h bar. So what I'm getting here is e to the minus or plus and plus I m q dot square dt divided by h bar, right? Now, what is this? Factor of, there's actually a factor of 2. Yeah. Okay. What is this?
The kinetic energy.
It's nothing but the kinetic energy, but written as a function of the velocity q dot, right? Times dt over h bar, and of course this exists together with e to the I v, or minus v, sorry, minus iv dt over h bar, and together, so after doing this integral for all the time steps, so at each time step I eliminate the p dependence, and I'm left with something that in the exponent will now have the kinetic energy minus the potential energy. And that's indeed the Lagrangian, right? Yes?
Doesn't it affect your formulation, the fact that you have dt now in the square root?
Okay, so dt is very good. So all of this will come into the definition of this capital D differential. Okay?
Yes, but you integrate over
now,
dt.
remember, we define dt, so you're worried about, okay, so again, it's well defined for any discrete number of states. Eventually you want to take the limit. If you keep it discrete, then what is dt? It's actually nothing but capital T divided by n, okay? So capital N will appear somewhere, okay? I'll write the final formula soon. So you'll get some function of capital N, and then you have to take the limit, and okay. But why don't I care about it? Because ultimately, this whole normalization factor is just a number. It's just a pre-factor. Okay? What is giving us all the physics is what's in the exponent. And what's in the exponent will be an integral over time of a Lagrangian. Okay? So let me write the final result. So, something. Okay, so here is what it is. G of Qi Qf t is going to be yeah, I'll write it like this. So it's an integral over a Q of t. We no longer have P, just Q of t, which is a trajectory. The integral is calculated under the constraints that at t equals 0, I have Qi. At the final time, capital T, I have Qf. And in between, I integrate over all possible Q of t's. I will define this in a minute, but the function that I'm integrating over is e to the I s over h bar, right? And s here is the action. S is in fact the integral from 0 to t of let me write it like this. It's okay. Let me write it explicitly. It's half m q dot square minus v of q. And this thing is nothing but the Lagrangian of q and q dot, where both of them are now functions of t, right? It's a functional of q and q dot. Okay, and now I have to define for you what is the differential, this capital D. Capital D is the limit for n going to infinity. Now I'm writing it explicitly in terms of the variable capital N, and it's the following expression. It's n times m over I 2 pi h bar capital T. I think I hope I don't miss anything here. Yeah, all right. 2 to the power n over 2. This 1 over 2 is because of the square root that we had before. Times a product, n goes from 1 to n of the Qn. That's what it is. Okay? That's the definition. Okay, so this is actually the final formula. What we got. Okay? And let us now understand what it means. So, first of all, it's a multi-dimensional integral, but in fact it's not only multi-dimensional. If you take the limit of n going to infinity to the continuum limit in the time axis, it's actually an infinite dimensional integral, and that's why it's called a path integral. It's a path. It's an integral. Not over a variable, or many variables, it's an integral over paths or trajectories. So, what does it mean? If we go back to this picture, and see what the propagator describes is we want to study the time evolution from a state we started at Qi and we do a measurement at Qf and we want to know what happens in the middle. Now, what quantum mechanics tells us, and this is the meaning, really the deep meaning of what we have here, is that quantum mechanics of a particle under a general potential cannot tell you anything definite about the coordinate between the initial and final state. So at any intermediate time, the wave function can spread over the entire Q axis, okay? And that's true for any time, but the time evolves continuously, and at each time we allow for Q to take any value. So what we're actually integrating over, we're integrating over all possible trajectories that will take us from Qi to, okay, we can think of a crazy, let's take a really crazy trajectory, okay, and right, and we can have a trajectory that goes like this, and there are infinitely many. Okay, all of them, quantum mechanics allows them, but it gives them a weight. Okay, it gives them a weight. So the action will give us, for each trajectory, it will give us something else, and whatever its value is, divided by h bar. Okay, you see that now this gives a dimensionless thing. So it will give us some weight for each trajectory. The final result can be thought of as an interference between all possible trajectories. Okay, so that's how we can think of a quantum particle. It's allowed to explore all trajectories, but the potential energy or the shape of the potential and the expression for the Hamiltonian will control what will be the amplitude or the probability. If you take absolute value square, eventually you will get the probability, but the amplitude is composed of a coherent superposition of all possible trajectories. Okay? Yes?
How it fits with the fact that the speed of light have a limit? I mean, we cannot suppress. I mean, if I can take every
no. So Q dot. So the what can take any value is Q. It's not Q dot. Okay.
Ah, okay.
But
okay.
you're saying, you know,
So I can take straight light.
Okay. Actually, maybe if you want to be really picky, I mean, of course, also this expression for the kinetic energy breaks down if you're approaching the speed of light. But let's not worry about it, because you know that in the end, you're going to get what is going to be the first of all, this is a mathematically exact result, okay? In the limit, as we say, and all that. But there's an additional thing we can say about it. You see, it's a very strongly fluctuating. If S is large compared to, or if the parameters of the system are such that it's large compared to h bar. Namely, if we had a particle that is relatively heavy and, you know, in the limit that h bar goes to 0, in the sense that everything else depends, everything else with the same dimensions is large compared to h bar. This is what we call the semi-classical limit. in the semi-classical limit, h bar goes to 0, or h bar very small, this exponent, this function, is going to be rapidly oscillating, and I think you know from mathematics course, I hope you know, that such integrals are dominated by a saddle point, right? Right? What is the saddle point? What determines what is the definition of a saddle point?
The second derivative equal 0.
It's dominated by the contribution where S takes a minimum, right? And what gives the minimum to the action?
Euler-Lagrange.
Euler-Lagrange equations, which dictates the classical trajectory. Okay? So, among all these infinitely many trajectories, there is one particular trajectory. I don't know how it looks, it depends on the potential, but maybe, something like this. Let me call it QC. Okay, for classical. The classical trajectory, this is what classical mechanics gives us, is what gives minimum to the action. And in the limit that h bar goes to 0, or in the semi-classical limit, it will dominate the integral, okay, and basically recover the classical limit. But we can do better, having this expression, we can do an expansion in h bar and get corrections, okay? So this formalism, first of all, it gives you, I think, a great deal of intuition that quantum mechanics is really about having a wave function that can explore the entire space, but eventually the laws of physics give it some weight, according to the quantum expectation values and all that, but we can smoothly connect to the classical, okay? And the reason that it's and actually the general result is always an interference. Okay, it's like a generalization of the two-slit experiments, if you like. Okay, but here we have coherent superposition of all histories to get to a point, from a point to a point. Okay, so that's a path integral. I already gave you an idea how we can mathematically deal with it in the semi-classical limit. So if you want to really study semi-classical limit, and it's very useful in problems like in the case where we have chaos, okay, when we have a chaotic system, then essentially you can get the effective, the classical trajectory, you can get quantum corrections systematically. All of that you can do with a path integral. Otherwise, I must confess, it's not very useful as a tool to solve a single particle quantum mechanics. Okay, it's not very useful. You'll see in the next week, Sal will show it in the tutorial. You will solve the problem of a free particle. So for a free particle, actually, it's easy to solve because there's no potential. You can also solve it for a harmonic oscillator because also there you have Gaussian integrals. Basically, this is, it's very difficult. I mean, you can also do some calculation for a linear potential, but it gives you, okay, this will give airy function, it's, okay. But as a mathematical way of approaching quantum mechanics of a single particle, it's not so useful. It's more useful from the conceptual point of view. What we'll see next, now we'll take a break, but what we'll see in the next lectures is that if you carry it on to many body problems, and for that we need some work to generalize it to many bodies, then it can become useful. Okay? Useful in the sense of solving problems, not just recovering what you know from other methods. Okay? Right, okay, so let's continue. So, up till now, what I described for you is a problem of time evolution of a particle under quantum mechanics, and I now want to consider a different problem where we want to do calculation, and we notice that there is a mathematical analogy between this time evolution problem and the problem that I will now consider, which is doing statistical mechanics, okay, equilibrium statistical mechanics. So before that, let me write down, probably I do it here. This is the expression that we got for the path integral, but I want to remind you the original definition of the propagator, which is the matrix element of the time evolution under Hamiltonian H between initial and final coordinate state, and with a time evolution t. Okay, t is total time. I just want to comment on something. Here I wrote propagator in terms of coordinates, initial and final coordinates. We can equally define a propagator which depends on an initial momentum and a final momentum. And of course it will have a slightly different form, but the idea is the same. Okay? So the Qi and Qf only serve to determine the initial and final states. Okay? Okay. So what is the other problem that I want to do calculation with? And this one will be actually mostly interested in the context of many particle systems. And that's doing statistical physics. What do we do in statistical physics? We want to calculate thermodynamic functions and physical thermodynamic coefficients like specific heat, compressibility, magnetization, things like that in general. And there is one object. So suppose we are in a grand canonical ensemble. We have temperature, we have chemical potential. Then we know that we can compute a partition function, the grand canonical partition function. And this will essentially give us everything. If we know to solve the partition function, its derivatives with respect to various variables will give us all the thermodynamic functions, the free energy, right? Free energies. So I'm just reminding the partition function, which we denote by Z, is essentially a trace over all states of e to the minus beta h. Okay, and here I allow h to be an operator. It's a quantum Hamiltonian, and h here will be the grand canonical. Actually, let me write it like this. Grand canonical is h minus mu n. Okay, that's general, and this partition function is is a function of beta and mu, where beta here is 1 over k Boltzmann T. So don't confuse it with the T of this T. Okay, don't confuse. Here T is temperature, but we're not going to use temperature, we're going to use beta. Okay? So I just write it here, and from this on we have only beta. Okay, so actually it's a function of beta and mu. Okay, and the free energy, or the grand canonical free energy, is going to be minus 1 over beta log z, right, and so on. So, and from derivatives of f with respect to beta and mu, we can get specific heat, we can get compressibility, we can get a lot of things. Okay, great. So, this is just a reminder. Now, so what is the partition function? It's you take an operator and you trace over all states. Now I'm talking about a quantum problem in general. And what is the trace? A trace is if you write the, if you take any basis, any complete basis, it doesn't have to be the basis of eigenstates because often we don't even know it. But if we take any basis of complete, but it has to be a complete basis of the system, then the trace is just the sum of the diagonal, right? Okay? So, in other words, we can write explicitly Z is a sum over lambda of lambda. Let me write grand canonical because for the many-body problem we really want to keep track here of or allow here fluctuations also in the number of particles. Okay? So here lambda is a complete set of states. I don't care what are these quantum numbers representing. It can be single particle or many body depending on the problem. Okay? Okay, that's the calculation. Now let's take the most simple example of a physical system for which we can compute the partition function from this definition is a single particle. Okay? So for a single particle, we don't care about the second term. We have only one particle, so it's not a constant. So let's just look at the canonical partition function, if you like. And now I'm rewriting it. Okay, so let's forget about all this. So now I'm looking for a single particle or a single degree of freedom rather, where H here is going to be exactly the same Hamiltonian we considered before. Just kinetic plus potential energy. It depends on only one coordinate and its conjugate 1 and 2. I want to write the partition function explicitly, where we just said the trace is a sum over a complete set of states describing this system. We can choose any basis, but in particular we can choose the basis of coordinate states, right? For a single particle, it's a well-defined complete set. Okay, so then the sum over Q is going to be an integral. Okay, so maybe we need some organization here, but it's basically this. Okay, it's it's integral over Q of Q E minus beta H. Okay. That's what we need to calculate. Now it's kind of stupid to do statistical physics for a single particle. Yeah?
Don't you need some factor for the units? Because the partition,
For what?
For the units, because the partition should be unitless.
You're right. There is some. You're right. I have to, but eventually, Z itself is not important. You know, there's an overall factor. If there's some constant, I don't care about it because all the physical quantities are log of this. Okay, so I don't. You're right, right? But I don't care about the units of Z. Okay, so you can write it like this. You can divide by something that sets the units if you're worried about it. No problem. Okay. Now. Again, so it's a little stupid. What I'm describing is a single quantum particle in a canonical ensemble, meaning that it's in an environment with a fixed temperature. That's the parameter beta. And okay, we can, from this calculation, we can take the log. We get the free energy, but it's. Yeah, it's a single particle. But the reason I'm doing it, I mean, we can easily, after we finish, you'll see that it's very easy to extend it to a many body or to a more, many degree of freedom problem, which is the case where we usually really want to solve statistical mechanics problems. Okay? Now, if you just look at the expression and compare it to my definition of the propagator, you notice a mathematical similarity, right? Because if I take Qi to be equal to Qf to equal Q, and here I have in the exponent, I have here an imaginary exponent, and it's h over h bar. You can easily see that if I replace I times t times h bar by beta, I basically get the same thing. So, in other words, I can I can actually replace this by an expression for the propagator with the appropriate mapping. And the mapping, notice, it involves also an analytical continuation from the imaginary axis to the real axis. So in other words, let us now consider a case where Qi equal Qf equal Q. And we replace beta by I t over h bar. Okay. Then this expression is nothing but g of q, and instead of capital T, I write minus I h bar beta. Okay? Yes.
Now, what is the physical meaning of the...
Okay, so what's the physics? So first of all, you agree with the mathematics. Okay. Now what it means is that we can basically, we actually know what this is. We have an expression for it, but the expression involves an integration over time, where here time is time. Time, it's a very real variable that changes between 0 and capital T. However, here, in order to play this game, we have to do an analytical continuation of everything, and we can introduce, once again, a real a variable tau. Okay, let me denote it by tau. Tau is going to be a real variable, okay, but it's going to be something that if I want to relate it to what I have here, I relate it by writing, let me just, okay, so, yeah. Okay, it's actually a mapping, right? I map the time t to an imaginary variable, which is minus I times t. Let me just see if we need, yeah, okay, so tau, it's minus I times tau. Okay, so tau and t have the same units, but what I've done here is rotate the time from the real axis to an imaginary axis. Okay, this procedure is called weak rotation. It's a rotation in the complex plane. Okay, so imagine that we extend the time axis to a complex plane where tau denotes the imaginary part. Okay, tau itself is real. Okay, but minus I tau is imaginary. Okay, so in other words, this expression can be associated with a propagator in an imaginary time. Okay? So what it means, of course, it doesn't mean time, but it can be viewed as a continuous variable that propagates us in some direction on an imaginary axis, and in fact, the way we are thinking of it is the following. So before we had some coordinate axis where we define our initial and final state, and then there was a time evolution axis. Instead of the time evolution, now we have another axis. Okay, this is a bit abstract. It doesn't have a direct physical meaning as an axis, but the end point of it, so what we are going to, we're introducing here a variable tau that interpolates between 0 and h bar beta. And the h bar beta has a well-defined physical meaning. Okay, it's just the inverse temperature multiplied by a constant that gives it units of time. Okay, so what we are going to say is the following. The matrix element that we have here, this diagonal matrix element, what it describes is an evolution in imaginary time. And this evolution is, you start from some Q, so let me call this Q prime, because here Q is a particular choice of Q. You start from some point Q, and when you are finished with this evolution, you go back to the same Q. Okay? Right? Go back to the same Q, and then in the end, to get the partition function, you have to integrate over all Qs. But basically, what kind of time evolution? It's evolution over some axis. It has dimensions. The dimensions are h bar beta, and you can think of it pictorially like a cylinder, because you are starting from a point, you evolve, and go back to the same Q, and then afterwards you integrate over the all Qs, and you get, so this imaginary time axis is the radius of the cylinder. Okay, so this is the right way of thinking about it. Actually, let me draw it a bit differently. You have here so we're starting from, for each Q, this is the Q axis, and this is, along this line, this is the tau axis. You're evolving in time, going back to the same point. Okay, so it has periodic boundary conditions, if you like, and then eventually you integrate over all Q. Okay, and that gives you and for each Q of tau, you plug in this expression, but you have to make the weak rotation going from T to tau. Okay, okay, so again, tau itself doesn't have a direct physical meaning, but it is a mathematical way of expressing a quantity that eventually does have a meaning. Okay, and that's this matrix element. Okay, and the advantage of this way of writing it is that everything here is going to be real numbers. They're not real, sorry, numbers, not operators, C numbers. Okay, you have to integrate over trajectories. Okay, trajectories in imaginary time. Okay, but of something that will reproduce. Finally, if you solve the integral, you found an expression for the partition function. Okay. All right, so let's do it. And in fact, it's really very easy to do the mapping because, again, we have already an expression. We have the result, right? We just have to plug in this mapping. Okay, so let's do it carefully. Okay, so I'm taking this expression. With your permission, let me erase the definition of the differential because it doesn't matter. Okay, it's some number, some expression that we anyway don't. You can read, you can plug in the original thing. Anyway, it had the square root of I there and things like that, so we don't have to worry about that.
Does it matter the sign of the rotation? Can it be positive?
Yes, it actually matters a lot, right? That's a good point. Why? Because in the end, we want to get a convergent integral. So for example, so this integral is, or whatever we get, eventually is going to an integration over a real exponent. And you want this exponent to be decaying and not a reversion. But you want the integral to converge, so that yes, it is actually very important to do it this way. Okay, and in fact you can also see that the mapping is between t's and positive t, and this is, this is the exact mapping. Okay, to get minus beta h. Okay, all right, great. So, okay, this we no longer need. So let's do the mapping carefully. So now I'm writing G of Q and T, and I just follow the definition. So I have an integral over, now it's going to be Q of tau, okay, for each Q, but here Q0 is the same as Q of the final tau, which is h bar beta. So h bar beta is the circumference of this cylinder. Okay? Okay, so we're integrating over a circumference and we equate Q of 0 to Q of h bar beta to something we call Q. Okay? Actually, if we then take this and integrate over Q, we even remove the constraints. We allow Q to be anything. Right? So from this to get the partition function, you get the same thing but without the equal Q. Okay? In fact, you know what? Let me just do it and write. Okay, you understand what I just said? Because for each Q, you have this periodic boundary condition. But then Q can be anything. Okay? So if I don't put it straight, I don't only get G of QQ, I get the partition function.
There is geometric phase in those processes?
The geometric phase? No. Why should there? I mean...
no, it's coming back to the same place. Maybe...
No, but it's... okay. So there is... So tau is not a parameter here. Okay? Tau is not a parameter of the Hamiltonian. What you're thinking of is some kind of a Berry phase.
Yeah.
It's... No, it's not. So we just have, a standard Hamiltonian. And we introduce here a variable and we do the integration under a constraint that it goes back to itself. That's actually very, very important constraint. But, there's nothing here. So what you get here, now you're integrating over something that I'll write in a minute, but basically that's it. That's a mathematically well-defined thing where d of q of tau, I don't write it explicitly, but it has the same meaning. It's basically an integral over infinitely many trajectories over this cylinder. Okay? But all of these trajectories, each of them is periodic. Okay? All the loops. Okay? Good? So, great. So now I have, what do I put in the exponent? So here I have S, and the exponent is I times S over H bar. But this S is written in terms of the variable t, and I have to change variables from t to minus I tau. Okay? So it's very simple. How do we do the mapping? If t goes to minus I tau, dt is mapped to minus I d tau, okay? And then this tau is going to be integrated between 0 and h bar beta, but there will be a factor of minus I outside the integral. Okay, this you already see how it will get to a real exponent. And now, very importantly, here we have q dot square in the kinetic energy. But q dot square, if we write it explicitly, it's derivative with respect to t, right? If we change variables from t to minus I tau, there's a 1 over minus I for each power of t, right? So it maps to minus the derivative of with respect to tau squared, right? So what we get from it is, if I plug these mappings into the expression I had for S, I get that e to the I S h bar, which is what I have to plug in here, is e to the I over h bar times a minus I, okay, minus I, integral d tau from 0 to h bar beta, and then what do I have inside instead of my Lagrangian, I have minus, right, because this minus d tau q square minus v of q. Sorry?
The m over q.
Yes, of course. Yeah, so, yeah, sorry, right? It's 1/2 m d tau q square minus v of q. Right? Okay? Now, notice the following. So, I times minus I is just 1. But here, both term appears with a minus sign. I can take this minus sign outside of the integral, and then I get something that I can write as e to the minus s a u, which is for Euclidean, where let me, so what is S Euclidean? Let me write it here. Plus v of q. Sorry, it's an integral. So it's an integral from 0 to h bar beta d tau of 1/2 m d tau q square plus v of q. Okay? This is called an Euclidean action. Why? Why is it called Euclidean as opposed to Minkowski, if you like? So it just denotes the fact. So what is the expression? If you pretend for a minute that tau is like a time, this is kinetic energy, right? And this is potential energy, but usually the usual Lagrangian is kinetic minus potential. The Euclidean action is kinetic plus, okay, it's a kinetic plus potential. Okay? In other words, it's the energy, if you like, but it's expressed in terms of coordinate and velocity and not coordinate and momentum. So it's not a Hamiltonian, okay? But it's, okay, so it's an expression where the kinetic and potential energy appear as a sum, not a difference, okay? So it's called Euclidean action, and you integrate it over this imaginary time. Once again, the upper limit depends on, it encodes the temperature. Okay? So let us put it into the expression. Okay, this is so. Oops, sorry. All right, so this is what it is. And this is the definition of Euclidean action. Okay? This I no longer need. Okay? All right, so you see that just from the definition, eventually if I compute the integral, and in some cases it can be explicitly computed. For example, if V is a harmonic potential, then we can solve the Gaussian integral. We can do something, we can compute it, but in any case, after we are done, what are we going to get? Something that depends on the parameters of the particle, the mass, and the parameters of the potential, whatever they are. But this imaginary time is just an integration variable. In the end, the result will depend on the parameter beta, which is temperature. Okay? And for a single particle, that's all you have. Right? You have, for thermodynamics, you have the parameters of the particle and temperature. Okay? Okay, so so this is statistical mechanics for a single particle, very silly thing, but we can very trivially extend it to a case where we have many degrees of freedom, or even infinitely many degrees of freedom. And let me bring it back, since what appears here is a Lagrangian written in terms of some coordinate q. We can think of a physical example of many body or many degree of freedom problem where we, in the beginning of the course, introduce a Lagrangian formalism to describe its field theory, and that's the case of an elastic string, right? Remember, this was our the first problem we solved, and then we used it to introduce A and A dagger and to form the basis for the second quantization. And all that we've done starting from a problem where we had not only 1 degree of freedom in our Lagrangian, but we had a coordinate that is a collective coordinate, like a displacement field, which depends on some fixed space value, right? Remember? And we didn't call it Q, we called it phi, but it doesn't matter, okay? So, let's go back to this problem. Okay. So we have some fixed axis x. Of course, we can also extend it to higher dimension, but let's just think of a single elastic string, a one-dimensional chain of masses on strings, if you like, which we take to the continuum limit, remember? And then we can introduce a collective variable, which is the Q. Let me just the displacement. So this is the equilibrium state, and we have some general. This is Q of x, okay? But this Q is not only a function of x, it's also a function of time, right? So we can, actually let me write it, it's a function of time, but this plot is for a fixed time. It gives you there is some disturbance generally, right? And we can write a Lagrangian that describes that is a function of Q and Q dot, right? And in fact, let me remind you how it looks like. So, or let me directly actually write the action. Now it's the real action, not the Euclidean one, but to do the mapping, we know how to do, okay? So, what was the action? This is something we already saw. It's an integral over time from 0 to some finite, it doesn't matter. And then there is also an integral over x, possibly up to some finite length, but it doesn't matter. It can also be from minus infinity to infinity. Of what? It's basically half m. Let me write it like this. Minus the potential energy, but what was the potential energy? It was half rho s. Remember, there's a stiffness times dx. Okay, that was what it was. And here Q is displacement field. Actually, in that case, we thought of a longitudinal, but it doesn't matter. Okay? It's some displacement of the string, which is a function of both x and t. Okay, and it's this integration over x is nothing but the continuum limit of a chain of many masses on the strings. Okay, all right. So this was the action, and now let us say, okay, now I'm not interested in the dynamics, in the real-time dynamics of this string. I'm interested in statistical physics. So at equilibrium, so time independent, I do the weak rotation in exactly the same thing. So instead of having just one q that is a function of t and I change t to tau, now I have a q of, q depends also on another variable, a space variable x, but for each x I have a q of t and I map the q of t to q of tau. Okay? So this is basically what I do. I take q of t and x and I map it to q of tau and x, where tau is defined as, where t is, here was mapped to minus I tau, and q dot, or dtq, for each x, or rather let's look at the square, is minus d tau q square, okay, and that's true for locally for each x. Okay, so for all the degrees of freedom I do this, and then what I get is a Euclidean action. So following this procedure, if I plug it into the definition of S, I get the Euclidean action of the string, which is integral from 0 to h bar beta, d tau, integral dx from 0 to length of the Euclidean, the Lagrangian, which is now 1/2 m d tau q square plus 1/2 rho s dx q square. Okay? That's all. And then what do I do with this? I now plug it in. Now I want to compute with this. I want to compute partition function. Okay. What I wrote here is the partition function of a single particle, but the partition function of the string is very easily extended. What we have instead of q of tau, now I have q of tau and x. Okay, so there's another variable that I'm integrating, and however, for each x, q of 0 is equal to q. So this periodic boundary condition in the time, in the imaginary time axis, are maintained for each x. Okay, so let me write the results then. So I get that the partition function of, this is for elastic string. Okay, so at temperature T, which is, okay, the inverse temperature beta, let me just write the definition. So this is going to give us an integral over all possible functions of tau and x, q of tau of x, under conditions that q of 0 is always equal to h bar beta for each x, okay? Periodic boundary condition in the time and whatever boundary conditions that you may also have on the x direction, okay? By the way, they could be periodic as well. There's no problem. So it could be a torus. Like if the 1D string is a loop, then you have two loops here. It's completely symmetric. And then what you have in the expression here is this Euclidean action that I just wrote down here. Okay. That's it. That's the. Let me actually rewrite it explicitly. So it's 1 over h bar integral d tau integral dx of stiffness times space derivative of q squared. Okay, this is it. This is what we need to do to get the partition function. And here the result is going, except of the parameters, which are here the mass and the stiffness. Actually, there is some velocity that you can extract and an overall scale, but another variable that it depends on is beta. This is for some temperature, okay, set by beta. Okay, and it's a very nice expression. Notice that we know how to solve this. Actually, if you actually want to calculate this integral for this particular very basic problem where everything is quadratic, first of all, you have here derivative with respect to x, derivative with respect to time. What do you do to make it look nicer instead of derivative? We go to Fourier, both in time and in space. Well, when I say time, the time is an imaginary time and it's a periodic variable by definition, but it doesn't matter. I can do a Fourier transform.
It's like Matsubara.
I will define Matsubara, but yes, but I'm going to go to Fourier space. This will give me some wave number here from the replacing the x, and in the time, the imaginary time, I get some frequencies. And because of the periodic boundary conditions in time, what can I say about the frequencies? The frequencies, they are going to be discrete. Okay? It's like a periodic function. Okay? So, but in any case, in Fourier space, the derivatives will be replaced by some constants, and if we take if we just replace it and do the Fourier transform, we get a sum over q and omega of something that depends on q and omega, and everything is Gaussian. So what you get here is just a multi-dimensional Gaussian integral, okay? Which is essentially a problem you probably solved already in statistical physics, right? So you've already seen it, but what I wrote here is, in a more general case, this is of course not a quadratic, it's some potential, okay? And it can have gradients in space as well as time. Okay? That's what you have in a general many-body problem. At least in the case where it's convenient to represent it by some coordinate and its conjugate moment. Okay? Okay, so here is how we go to a many-body problem, and of course, so there is, by the way, it's very easy to extend it to higher dimension for the same problem of elastic or whatever, instead of, if you don't have just one-dimensional space axis, you have some three-dimension. Everything carries the same, except that instead of integral over x, you have integral over r, and q will be a function of r vector and tau. Okay? So you can basically extend it to, generally you're going to get, let me write a more general Euclidean action that is going to be something like integral d tau and integral d-dimensional integral over space, where this integral is over some volume, if you have a finite volume. This integral over time is over from 0 to h bar beta, but with periodic boundary conditions. So it's some kind of higher dimensional cylinder, if you like. And inside here, what you have is will be some kinetic energy, which involves. So let me write something that will be most general. The kinetic energy is some function of time derivatives. Okay, this is a function. Okay, and there is a potential energy that is a function of q and its gradients, space gradients. This is generally the form. Okay. I want to stress something very nice about the quadratic version of a string. If you look at space and time here, x and tau, and let me even go further to the case where the space dimension is also a closed loop. So it's a ring, and in time you also have a ring with a radius or with a circumference h bar beta. And notice that space and time are completely symmetric. They appear in a symmetric way. And I can change variables since some combination of rho and m give you a velocity. There is a velocity, right? So it's basically the square root of rho over m. And I can change variables, so I define a y coordinate to be this v times tau. Okay. And then I change variables, there will be a factor of v somewhere coming in, and I will have some length in space and some length in time. Okay? And space and time appear completely symmetric in this expression. Okay? So, and now if I can now imagine that I add some non-trivial additional terms to it that are non-Gaussian, and I can get from it a phase transition. Like basically what I'm writing now is kind of a Landau theory, a Landau-Gibbs theory for a field Q, which is a function of R and tau. And the Euclidean action, in the Euclidean action, the time and space are, or if you like, the time direction, the imaginary time, is like an additional coordinate, right? It's like an additional coordinate, and this integral can be thought of as an integration in d+1 dimensions of some higher dimensional space. In the case where the limits of this integral are infinite, that's where we can talk about thermodynamic problem, where we go to infinite length, infinite volume in both time and space, for that to describe some macroscopic system of infinite size, we need beta to go to infinity, right? What is beta going to infinity?
Zero temperature.
It's zero temperature, okay? So, what I'm basically saying is that if you have a system, a many-body system, or some physical system described by a field theory, and you want to describe its zero temperature phase, or zero temperature quantum state, then it is equivalent to a classical problem in d plus 1 dimension. Okay, so in your classical, statistical mechanics classes, I think you've seen Landau theory. You learned it, right? What is the free energy that you put in the Landau theory? It's an integral over space with a factor beta in front, right? This will give you a classical theory that may, for example, describe a magnetization transition. Okay? Now, however, if you are accounting for, so what is it? Let me just show you that here, if I take this Euclidean action and take the opposite limit, that beta is not going to infinity, but beta is small. Beta small is high temperature. At high temperature, this integration, because the tau is very short and Q hardly changes, the high temperature will just give you, this integration will just give you a factor of h bar beta, right? And the first term will vanish. Okay, so the dynamics will not play much role at high temperature. What you care about is only the potential energy. And there will be a prefactor h bar beta that then, if you plug it into the exponent, it will cancel with a 1 over h bar, and you get beta times the classical free energy, right? Okay, so that's the high temperature limit. And that gives you a statistical mechanics of a system at little d dimensions. But if I go to the t equals 0 limit, 0 temperature, which is like beta going to infinity, I can introduce a hyperdimension capital D, which is little d plus 1. And I get here a theory that is equivalent to a classical model or classical field theory at one higher dimension. Okay?
And for example, for this quadratic term, we will cover, for example, the viral theorem and things like
right.
that. Everything
Yes.
like that from
That's
statistical
right.
mechanics.
That's right. Yeah. So everything you know from the statistics, but most importantly, you can get. So, for example, you can start from a two-dimensional problem in statistical physics. For example, the two-dimensional Ising model. Okay, as you know, I don't know if you learned it. Did you learn it in any course? The two-dimensional, not the one-dimensional. Because one-dimensional you can compute the. But in two dimensions, it's actually there is a transition, okay? There's transition from a paramagnet to a magnet, which in one dimension you don't have for a classical model, okay? But if you have a quantum model for the Ising model in one dimension, because the time dimension gives you an extra dimension in the analogous classical problem, you get a transition, okay? So you can get a transition from paramagnet to magnet for a one-dimensional Ising model at 0 temperature. And this is called the quantum phase transition, okay? So this is just, all I said now is a bit beyond the course. Actually, if you are taking my course next semester, this is going to be one of the topics. But here you can see where it's coming from. Formally, it appears like there is just another dimension, okay? And that's time, the imaginary time. Okay, so questions about this? Okay, it's just any questions? Okay, so the last thing I want to say today is I'm now getting really to the many-body, the more general many-body case, because all I've done here is I started from a single particle and I extended it to a many-body, but I did the many-body for a particular problem where it's convenient to describe everything still with coordinate and momentum. And that's the case where the elastic string is an example of a many-body or many degree of freedom problem where you have a displacement field is naturally some coordinate and there's a natural momentum. But we know that even for that problem, to simplify it, we notice that it's useful, first of all, you go to Fourier space and you get the modes, and even when you go to K-space, you see that the most compact representation, even of that simple problem, is by mapping the Q and P to A and A dagger, right? And that's for a very specific problem where I already showed you how to do a path integral formulation. Now let us ask another, we want to solve a much more general problem. We have some interacting particles, quantum particles, bosons or fermions. They are described by a Hamiltonian. The Hamiltonian is written in terms of what? A and A dagger, right? That's what we learned all through the first part of the last part of the course. We learned second quantization, and we know that in order to write any quantum mechanics problem of many-body, the useful representation is to introduce a set of quantum numbers and annihilation and creation operators and the vacuum on which they act. All that we already know. And now what I want to do is, okay, take this Hamiltonian, which is a function of A's and A daggers. Let me call them A alpha and A daggers. Okay, it's some combination of this. It has one body, two body, three body, whatever. Now this Hamiltonian, this quantum Hamiltonian, I want to plug into the definition of a partition function and do statistical physics, do finite temperature, compute thermodynamic variables. Okay, so the problem we want is to be able to compute a partition function, a grand partition function, which is a trace of e to the minus beta h grand canonical. But now our Hamiltonian so our Hamiltonian H grand canonical is some Hamiltonian minus mu n, where H is written in terms of A and A dagger, but also the number operator is also naturally written as sum over alpha of A alpha dagger, A alpha, right? This is and here A and A dagger represent annihilation and creation operators of some quantum particles, either bosons or fermions. Okay? That's in the case that you have only one type of particles, identical particles, and alpha are the quantum numbers of the whatever quantum states they are for the single particle basis. And that's what we want to compute. And as we saw in the examples I gave you earlier today, we should be able to express this as a path integral. And it may be useful for some things, because a path integral is an integration over some functional where there is the general form will be an exponential of an action. Okay? But what is that, and what is the advantage of a path integral? That we don't have to worry about commutators anymore. Okay? The commutators are somehow buried in the dynamical expression, in time derivatives. Okay? It's not that they disappeared, but they are buried there. Okay, because all we did, for example, the fact that we had this going like, okay, an exponent of e to the I pq over h bar, this encodes the fact that p and q are conjugate variables that obey canonical commutators. Okay, so it's not that the commutators disappeared, but we replaced the mathematical operation that we have to do into integration over C numbers. Okay, and that's a huge advantage because the commutators of a general quantum, many-body quantum Hamiltonians can be very complicated. Okay. Now, what is the problem, though? That we saw how to go to the path integral representation in the case where we started from a problem well defined in terms of a coordinate and momentum. But that's not what we have. What we have here are A's and A dagger. Okay? So, we need to develop a path integral formulation in terms of these operators, but with the same philosophy. What was the philosophy? If you go back to what I did earlier today, the philosophy was, I took the operator, I broke it into small pieces of time evolution, but eventually I had to introduce a resolution of identity, which allowed me to replace it by matrix elements of these operators in some very useful eigenstates. What were the states? The eigenstates were Q and P. What is the advantage of Q and P? Why P and Q? Because the formulation of the Hamiltonian was in terms of P and Q, right? Now, the variables are not P and Q, the variables are A and A dagger. So what we want is to introduce states that, just like in analogy with these P and Q, are eigenstates of the operators A and A dagger. Okay? And there are such states, and these are so-called coherent states.
For
Okay.
just for A, right? Because for A dagger,
Yeah, you're right. Yes, we can actually, it's enough to introduce them for A, and A dagger will follow. So that's exactly right. So what, let me just start the definition, and of course we'll continue next week. It's getting late. So I'm going to introduce coherent states, which are the following. First of all, let me introduce a variable phi, which is a vector of a number of infinitely many components, each corresponding to the quantum numbers alpha. Alpha are the single particle basis over which we define our A and A dagger. Okay? It's a complete state of single particle states of some kind. Doesn't matter, momentum, latticite. Okay. Okay, so this is just the definition of what I call phi, and now I want to define a state phi is defined, this is a coherent state labeled by phi, where phi is actually a set of numbers, it's not just one number, which obey that for any alpha, A alpha acting on phi will give you one of the components, the component alpha. Okay, in other words, so this is, if you like, a definition, I don't know how to, okay, that it's an eigenstate of the annihilation operator. Definition. Okay, that's what it is. It's an eigenstate of the annihilation operator with eigenvalue phi alpha. Okay? So, how do you write it explicitly? So definitely, first of all, you can easily convince yourself that phi cannot be a Fock state. Remember that we usually, up till now, or in the earlier part of the course, we worked in a basis of so-called Fock states, which are product of alpha of some A dagger alpha to the power n alpha acting on the vacuum. These were Fock states, where in a Fock state there is a well-defined number of particles. But a Fock state cannot be an eigenstate of annihilation operator because, by definition, the annihilation operator always reduces the number of states. So it cannot be a well-defined number. It must be a very elaborate superposition. But in fact, there is something you can easily convince yourself, and in fact you will get it in your homework to prove directly that I can tell you exactly what is, I can express phi in terms of A daggers and so on, and it has the following form. it's the exponent of acting on the vacuum. Okay? So it's yeah, that's what it is. Okay, so if you take this expression and apply A alpha, notice this here in the exponent I have a summation over all alpha. Okay, but if I apply a particular A alpha on this, I'm going to get exactly what I want here. Okay, this can be proved directly. Okay, so that's a coherent state, and you can easily see that not only it's not a Fock state. If you open up the exponent, it's an infinite series, right? So if you expand it, you get a superposition, an infinite superposition of all possible number states, right? Because each term in the expansion will have a higher number of daggers. So in fact, it is kind of the superposition of all the possible states that you can create with a dagger acting on the vacuum. Okay, that's what it is. Now, I should stress something very important, that this coherent state is, and everything that I do next week is for bosons. Okay, so here when I wrote A dagger, previously I told you we want fermions and bosons. This is true. This definition and this definition are correct for bosons, namely okay, oh, let me write it here. This for bosons. Okay, well, for bosons, I have that these are the commutators. I have some delta, alpha prime of A dagger, commutator. Okay, and of course, A dagger will give 0. But these are commutators, not anti-commutators. And in this expression, this phi or these phi alphas are complex numbers. Okay? Phi alpha is complex, a complex number. And in fact, you can easily see that if I take this equation and I dagger it, I take the Hermitian conjugate of it, what I get is, let me just do this. Okay, so if I take this equation and I do the Hermitian conjugate on both sides, on the left-hand side, I'm going to get a alpha dagger acting on the left on phi that equals phi bar. Okay, well, phi bar, this is in this part of the course will denote just the complex conjugate. Okay? So yeah, and it's easy to. Why did I say in the first place that phi alpha is a complex? Because A alpha is not a Hermitian operator. it's not Hermitian because its conjugate is different operators, so its eigenvalues are not real, they're generally complex. Okay? Okay, great. I think this is a good place to stop. And what we do next week is to use these coherent states to introduce resolution of identity, everything we did for the path integral of the Q and P thing, we'll repeat, and we'll do it quickly because we already learned the trick. It's the same trick, except that now we're working in a basis of coherent states. Okay? And then you will get something that is at the end kind of similar to what we got before, which is an exponential of an action. Okay? Okay, so yeah.
Thank you.
See you next week.